Recording in progress.
All right. All right. So these are the same links from last week, as it's the same locations. So I had given you the Q learning example. I'm still going to continue using Frozen Lake, all right, to be consistent. I may at some point do taxi cab, and taxi cab is nicer because it's like it does have a little simulation, but I think Frozen Lake is simpler to understand. Okay. And also let's click on same link for the code. Right, and this goes to deep learning, second edition, reinforcement learning. So here I have, so last week we covered RLQ lookup table, as you can see. And then today we're covering Frozen Lake NN ran RL. All right, so, but it's very similar. Like the environment is exactly the same logic. We just really need to comprehend or understand how we replace the table with a neural net. And then how do we actually, the loss function, right? So how do we address the loss function? So I'll start, so I'll need, a Jupyter notebook for this one. All right, so I'm not going to repeat this as I covered these ideas last time we met, but, just this is the Frozen Lake game, right? And we went over that. Remember before we had a table, and essentially we have, because it's a board game, we really just have 16 positions, which can be one-hot encoded. And that results, a vector of size 16, and it's one-hot encoded, essentially. So given a state, we want to select which action to choose, right? So we want to up, down, left, or right. That's essentially what we're doing. So now what you need to try to imagine is how this can be replaced with a neural network. So this table that you see here gets replaced with a neural network. The neural net can have however many layers you want it to have. What really matters is the input layer and the output layer. So the input layer is what? The state. And the output layer is what? The actions. Do you see that? So if you think about it then, it's basically the input to this neural network would be a vector of size 16, right? That a vector of size 16 indicating the state becomes the input to it. And then however many layers you want in there is fine. The output, though, needs to be a vector of size what? 4. 4. You have 4 actions over there, right? So now you want a neural network that will tell you maybe the probability that it should be up, down, left, or right. It's like a classification problem, essentially. You see that? So this is very similar. What's a little bit different is the loss function and how we're going to train for that model, the Q value. All right, so that's essentially the background of it. We've already covered the idea of the Bellman equation. And of course, we went over the code last week. So today I'll just go over it again. We'll go over that. So this is all so that's basically, we covered, I would imagine, until here last Wednesday. So today we're picking up here, okay? So now that we understand the Frozen Lake, so this is called Q learning using a neural network. Okay, now that we understand the Frozen Lake game with a table, we can proceed to replace the table with a neural network, okay? It is important to note here that the weights matrix in the neural network could be thought of as representing the Q values, essentially, right? So, that's the information we are going to try to learn. Otherwise, just think of the neural network as the table. We give it, as I said, the states, a vector of size 16, as its input, and the network predicts actions, a vector of size 4. All right, and this way you can build essentially anything. You could build a self-driving car, if you want it, with a neural network such as this one, right? So imagine now that self-driving car might have a camera, so that's a whole bunch of images, and then you spaghettify them, and they become really big vectors. So this was done in the Atari game, when they used Q-learning for the Atari games, that famous paper by MNE, in I think in 2015 or so, they did something very similar. So I don't know that I added that paper, but yeah, that's an important one. So essentially, you can think of it, you can give it images or whatever as input, and then predict what action you would take in the game controller, right? Atari had a joystick. And so, but anyway, in this example, we're keeping it very simple, just representing the board game, the 16 states, and predicting actions. If you're curious to see this extended to a bigger thing, I would recommend that on Netflix, I believe, or one of those, there's a documentary called AlphaGo, and you can check it out, and you can see how Q-learning, deep Q-learning, was implemented to build a system that defeated the champ in Go. The game of Go is like chess, and so the documentary is called AlphaGo. A very, very important paper in the history of reinforcement learning. All right, so as you can see, the code will be very similar. We're going to use PyTorch, of course. If you've taken 520 already or 365, this is going to be very familiar to you. And so we're just going to build, very simple neural networks. Here you can see I have a little bit of a graph just to kind of indicate how the neural net works, right? So you can see we have an input layer of one hot encoded vector of size 16 and the output vector of size 4. And then this is essentially a logistic regression algorithm, or a neural network, I should say. But you can imagine how you can add as many layers as you want in between and make it as deep as you want. Okay, so in my example, I probably have just like a multi-layer perceptron, but we'll play with it a little bit, and we'll print out a few more results this time around. Essentially, remember, in reinforcement, so in supervised learning, we always want to minimize the error, right? So the loss, we always wanted that loss to go down. With reinforcement learning, one key thing is we want to maximize the rewards. So we're getting rewards every time that we do things. We can even get penalties, and those are just negative rewards, if you want to think of it that way. But the goal is to kind of see those rewards go up, right? So that essentially, when you measure the performance of a reinforcement learning algorithm, a lot of the time it's in terms of seeing those rewards going up. And then hopefully that reflects in the game being, or the agent being better at the game. Okay? So yeah, so this is the code. Obviously you can read through this, and my notes on trying to describe this, but I'll demo it in class today. And the tricky part, I would say, is probably the loss function. Plotted, and then here's the randomness performance. I'll talk about that too. That's important. And then you can see this is the objective. I have this graph, which we will try to generate also. I'll show the code on how to generate this graph in the example, but essentially that's the rewards over time. So as you can see, the goal is for those reward values to go up. Do you guys see that? So that's essentially what we want to do. This is also, you plot this, the number of steps and so on, okay, of successes. All right, so I leave these notes for you guys to read through, okay? And now we can just go ahead and proceed to our Jupyter notebook, right? So I'm going to go ahead and start Jupyter. Oh. Prompt. There. There. Bring. All right, so We did RLQ learning right there, so I'm gonna do a new one this time. So Conda environment list. Okay, it should be. Were we using the 2024 one? You guys remember if that's what the one we were using? I think that's the one I used last. Yeah, so Conda, whoops. I did clear out a lot of the environments last week. So Conda environment, Conda activate. I 37, 530, 20. All right, great. All right. So remember the script. Oh, and I should have started. Okay, so RLQ learning. Right, this is the one that we did, so I'm going to create a new one here. Okay, let's add a few cells. And I'm going to change the name to DQN. DQN for Deep Q Learning, Frozen Lake. Right, all right. Okay, so let's start with a few basic things. So DQN. Right down. All right. Okay, so remember this is, this is the link, the location. This is what we did last week. So today this is the exact code I'm going to cover. And we're just going to go through it in depth. Hopefully, should be good. Let me. All right, so Frozen Lake RL and NN, guys. So we've already installed these libraries, but I'm going to copy them. So essentially, Jim from last week, NumPy, right? Random. You can see that now I'm going to start building a neural net, which essentially means I need Torch. I'm going to have matplotlib for my plots, and then torch nn, so I can instantiate classes, torch nn functional for any loss functions. The loss function is is a smooth L1 loss. It's kind of like MSE. So it's the absolute, it's actually a loss that sometimes it can be MSE and sometimes it can be absolute, the absolute mean. So we can look it up. All right, but it's essentially like an MS. So torch NN, torch functional SF, and torch opt-in, basically. So the classic things that we always use to instantiate a neural network in PyTorch. So we can go ahead and run that. Okay, so this one doesn't have a torch. Strange. Pip install torch. All right, while it's doing that, those are the libraries. Then if you notice, the parameters are going to be very similar. Steps list, how many, remember in reinforcement learning, we want to keep track of how many steps it took to solve the game. Rewards list, we want to keep track of the rewards that we're collecting as we are training. So initially we might get a lot of negative or zero rewards. Eventually though, as the algorithm is learning, the rewards should start to go up. You guys see that? Success list, that's another list of like when you win the game, how many wins you had. Since we're gonna do this in this one, we're not just playing like one game, you're playing multiple games and taking an average. We've talked about the parameters for the updates, like the learning rate, Y, the number of episodes is the number of games that we're gonna play, and so on. So I'll copy these parameters, and then we'll get, all right, so torch finished. It's good. Let's see if it works now. Okay, let's add the parameters there. And we're also going to add these from last week. All right, seems to have installed it. Let's try it again. Hit run. Let's give it a minute there. All right, it finished. No errors, so everything should be working now. That's good. So let's go over the lists and the parameters. All right, here we are. So now the next thing is we're going to need, so you can see really quickly, we're going to get into the neural network architecture, right? And then we just have to learn how we're going to use it. But this is essentially our model, our agent, etc., whatever you want to call it. Keep in mind that the terminology as we are moving into the world of reinforcement learning, when we're using these neural networks, is to change the name from model to agent, right? And so that's kind of how you see the terminology. Now, we're going to build our architecture, but if you notice, we need a utility function. And this utility function is just so that we can create that input vector, right? So we're going to have it's still the same game, right? Frozen Lake, and we still have 16 states, right? So once we, let's say we're in state 7 or we're in state 3 or whatever it is, we're going to need to one-hot encode that. So if you remember, the gym environment would return the state as a number, like a 3 or a 5 or so on, and we just have to convert that into a one-hot encoded vector. But I will demonstrate this right now. So we're going to have this utility function, gen state vector, and we're going to analyze it. So if you look, gen state vector takes in S, right? And then we're going to create with NumPy this thing. We're going to use the function NP entity identity of size 16. Okay. And then this essentially is a complicated way of saying what value should have a 1, what value should have, and what other value should have a 0. So I'm going to demonstrate how this works. So let me grab gen state here. So I'm just going to demo its usage. So imagine that S is something like, let's say you're in state 3, right? You're in state 3. So 3 will go into gen state vector, right? And that means it goes into this function. So initially this function states NP is just the actual vector, but in NumPy data structure. So then from there, we're just going to change the type to be a float 32, okay? And that gives us, just modified that vector. And then finally, remember, since we're building a neural network in PyTorch, PyTorch will not take NumPy tensors. We have to convert them into PyTorch. All right, so we do torch dot from NumPy state NP. That creates this variable inputs 1, and then we just return inputs 1, which essentially should be a torch and tensor. All right, so let's demo this one. Okay, generated the function. And as you can see there, it is a torch tensor. Remember, it starts at 0 with indexing. So it's 0, 1, 2, 3. Do you guys see that? Does that make sense? All right, and so we can change that to a 7, and the 1 is going to be over here somewhere. And there it is. We can change it. We'll do one more to 12. And there you go. The 1 is over here, and everything else is a 0. So it's a one-hot encoded vector of the state, and that's the input to the neural network. All that happens with this value, it comes from the environment. Wherever we are initially, we take an action, and the environment is going to tell you what state we're currently in after taking that action. All right, sounds like it makes sense. So now we can actually proceed to, instead of creating the Q table, we're just going to create a neural network. So I'm going to go ahead. And I have several architectures here. As you can see, I have this one, which you should know. You should be able to tell me the name of this one or this one. And I just did 2, but you could have done many types of architectures. So I'll do both, and we can discuss them. So I'm going to grab this one first. There we go. That's, something QNNet, right? As you remember from 520, you instantiate, this is class inheritance. So you inherit the NN.module. This is most of these have this format, the constructor. And then they have, or 365, or the forward function, right? So they have this approach. So here I have, in the constructor, we initialize the NN.module and also this class, and we specify the elements to build a network. So I have NN linear, and notice over here, it goes from 16 to 4, right? You can see that from the size of the input vector to the size of the output vector. Okay, so that creates linear 1, and then linear 1 will just go through a softmax, as it is a type of classification problem, which it creates a probability distribution that adds up to 1. Exactly, very good. All right, so now you can see here in the forward, the S comes in, the input vector. So actually the integer comes in. We have the gen state vector, which is our function that we just defined here. You can just add that in there. So this will create our torch tensor of size 16. Then our torch tensor of size 16 goes into linear, becomes this X, and then this X goes into activation to produce Q out. And that's it. So remember, at that point, it is softmaxed. Okay, it is softmaxed. And then this essentially, it's a squeeze operation to change the dimensions that it might have. The batch, I think it's the batch size that's in there. Remember, there's a batch size that's associated with this. All right, but we can take a look at what it looks like before and after. So this is the neural net. This is the one architecture. It's not a deep neural network. It's not even a multi-layer perceptron. In fact, there are no hidden layers in here. It's logistic regression, essentially. Okay, any questions? Pretty easy, right? All right, great. So now let's look at another neural net, just so that you get kind of the gist and how you could extend it to deep Q learning. So we're going to go over here. So this is another, did I run? Yeah, I ran this one too. Okay, so this is another architecture, same ideas. This one, though, has one layer in between, right? So if you notice, we do 16 to 10. So 10 is going to be the hidden layer, and then 10 to 4. So it's a multi-layer perceptron, or MLP, and it's got the softmax. So you can see it's the same idea. The state comes in from the environment. It gets one hot encoded to produce X. Then X goes into a linear. That's from 16 to 10. Then that X goes into the activation function, which in this case, it's a ReLU activation, but you can play with tangent or sigmoid and experiment as you wish, right? So, it's a hidden layer with activation. That gives you X over here. Then that goes into linear 2. And that's going to be this architecture here from the hidden layer of 10 to 4, the output layer. Okay, and then that X goes into activation 2, which is that last layer, which is softmax for this type of problem. That gives you Q out, and then we do the squeeze once again. And that's our neural network architecture. So instead of a Q table, now we have a neural net to given input states to predict actions. Questions? All right, great. So making sense. And now that we have it, then that's, we just have to bring in the code that we had from last week of Frozen Lake to kind of, interact with that environment. And then we just have to figure out how we're going to optimize, right? See, that's the other hard part, the optimization of this. So let's go ahead and move the next section. So now we're going to start instantiating the environment. So I'm going to create the gym environment. Okay, so okay, that ran. And then I'm going to just instantiate a couple of things here. We can do, I'm going to use the MLP in this example. So that's going to be my model or agent, however you want to call it. And the optimization now, it's going to be opt towards optim atom. Remember that you take the model weights and you tie them to the optimizer, and then the learning rate as we defined it. Because we need to learn the weights for this one, so we do need a learning rate. All right, so let's go ahead and instantiate these elements. All right, so they should be good. Okay, so now we look, the main loop, which is almost exactly what we were doing last week. It's got a little bit more, but it's, because of the training, or the loss function. So I'm just going to copy this one. So we debugged it last week, so everything should be good now. But I'm still going to go through it. A lot of it is similar, but I will go through it. Right, so here we are with this one. Okay, so let's take a look. This is going to have some ideas that I will address later related to the randomness. So one key thing about this model is, remember, whether it's the tabular, the table, or the neural net, initially the weights are 0, right? So it doesn't really know what to do in the beginning. And so you want initially, something called exploration in reinforcement learning, where you want essentially the model to just kind of explore, make random choices and see what happens. And as time progresses into training, the assumption is that the weights are better, so you start relying on you don't rely on that as much, and instead you just rely on your neural network or your table. So that's what this parameter is for, but we can come back to it. So let's start here. So initially, we have one for loop, and then we have this while loop, if you remember. This is the training phase. And so what we're going to do here is we're going to play the game, right? Multiple times. So that's what number of episodes is. I think it's set to 4,000. So it's essentially like saying I'm going to play Frozen Lake 4,000 times. Okay. And during that process, I need to learn, the weights correctly. So this is similar to what we did before. If you remember, we call the environment, we reset it. Whenever you reset the environment, because you're starting a new game, it provides the state vector, the initial state vector, where you are in the frozen lake. If you remember, it gives you a tuple. So the environment returns tuple, so select the first of tuple. So this was one of the problems we were having last Wednesday, but here, it's fixed now. So this will give us the state, some integer. Our roll is set to 0, so that relates to the some accumulation of the rewards. Remember, D just means it's a flag that tells you if the game is over, whether you died or you win, it's over, right? So initially, the initial state is false, so it means the game is still on. J is just a counter to keep track of the number of steps that it's taking for you to play the game. Okay, so that's the parameters here. This one over here is just to print the progress. So since we're doing 4,000, it'll print every few iterations, and it'll just print what game it is out of however many episodes you have. All right, so once you get to this is like the really important part where we start for each game, we start playing it. And as you can see, we have about 1,000 iterations, right? So we can almost like if I'm playing a game, that's the number of lives or whatever it is. Although you may die, that's actually a bad analogy, but it's the number of times, the maximum number of tries that you can have in this game. If you notice, this part here is related to the randomness, okay? Reinforcement learning is really big on this part. It's really important. Trying to think in GPTs, in all kinds of things, this is really important. The exploration phase, right? You don't want the model to get stuck in some area, just one thing and it's not really exploring the whole game space. Obviously, this game is small, but there may be games that are much bigger, and so the game space is much larger, right? So that's the idea. So if you look here, the idea is easy. So we have an if statement here, and the if statement is checking this epsilon value, right? It's generating a random number, and the epsilon value is changing. So the way that it works is that initially, it's going to select the action from the action space kind of randomly, okay? So it checks it randomly. Over time, as the game progresses, it's going to use this a lot less, okay? And instead, it's going to use that, okay? Which is to actually use the neural network. If you notice what happens here is we have model. This is the neural net, okay? This is the neural net that we instantiated here. The neural net takes in the state, S, as an integer. It detaches it from the graph, the PyTorch graph. And this may be because it was giving me an error, and so that is yeah, sometimes if you did, so what I wanted to say is if you detach sometimes and you shouldn't, you might be affecting training. So you have to be careful with this detach. But in this example, Hopefully it's okay. All right. So anyway, so it is detaching the result. So this model predicts an action. It assigns it to QS. And then from here, remember, so torch max here grabs from QS, and it returns two values, one of which is the maximum index. So it would be essentially the action, right? So if you have a vector, 4 values, the index of it, which is equivalent to saying the action out of the 4. And then that max index is assigned to A, and that gives you the action. So you either randomly select the action or you select it from the model. Do you guys understand that? And just keep in mind, initially, this math logic here, right here, this is just selecting a random value every time, right? But this is the value that's changing over time so that it's eventually this random number will start to be greater than epsilon, and therefore it won't go into that part of the if statement, sorry. Okay? But we can print these if we want just to see the behavior, but it does do the job. All right, so that's how you get the action, either randomly or from the neural net, right? So before we were getting it from the table, now we get it from the neural net, so that's easy enough. Once you have the action, you plug it into the environment, take a step with it, and if you remember, it returns 5 parameters, which we discussed last time. The reward, if the game is over or not, and S1, which is the new state. So remember, you're in a state, you take an action in the game, so now you're going to end up in a new state, right? Somewhere else in the board. And so now you have that information. Additionally, if D equal true, which means you either won or died. Yeah, won or died. But the rewards are 0. Actually, this makes the rewards penalizes even more by providing a negative reward. Okay. So now that that's done and we've taken that step, we need to start looking at the part of calculating the loss function. So this is going to be the training of the weights. Okay. So we are going to use f.smooth L1 loss, which is what I was saying. So this is a loss function like MSC, but it's like an if statement. It looks at a specific value and it just selects it if it should be a square difference or an absolute difference. So it's called the L1 loss. It's similar to MSC. So if you notice here, it's going to need 2 parameters, which are QPred and target Q. So we're going to calculate 2 values and take the difference, take the difference between them, and then we get this loss value over here, and then this should be similar. So the key question is, how do we get this QPred and this target Q? So let's take a look at that. So I'm going to create that for one, and I have this QPred for the other, right? And these are the values that we're going to compare. So let's kind of try to compare them a little bit. And notice it's essentially trying to also use the Bellman equation. Okay. A little bit. So let's compare them. So let's take a look at the bottom one first, because it seems to be the easiest one, right? So if you notice, the bottom one takes in the state, not the new state S1, but the old state S, right? If you look, the old state fits it into the model. The model returns a vector there, right, of size 4. And then we pick, given the action that we took at state S, right, the value. So it gives you QPred. Do you guys see that? So it's the reward essentially value, not the action. Do you understand? We take the reward, not the, so the vector contains rewards. And then if we pick the highest reward, we would get the action to take. But here it's using the actual reward value. Got it? So whatever the reward was for the state and the action that we took. Okay? So that's QPred, and QPred is what goes in here. All right, then for the other one, the thing that we compare to is going to be same neural network. You can see it's our model, right? Our neural net. But we provide S1, which is the future state. So we are in state S, we take an action, and now in the environment, we end up in state S1. So you can see this is the future value, okay? S1. So that gives us QS1, okay? And if you look, we have a vector there of size 4. Then we run it through a torch max function, and that returns max QS1, which is what? Is it the index or the reward that we have in max QS1? That index. This was, so remember, this was actually a reward, correct? So we need to compare apples to apples. So this is also a reward. Do you see what I'm saying? Does this make sense, guys? And then if you notice, the next step is to take this R and add to it this max QS1 multiplied times some parameter, which in this case is basically 1, right? It's 0.99. What is this R here? It's a reward, right? Which reward? This one up here. So remember that when you're playing the game and you take an action in the game, you know, you're in state S, right? You're in state S here. And given that state, it tells you to take this action. So then you take that action and you plug it into the environment. You take a step in the environment, and now the environment moves you to another step, but it also gives you a reward for this game, because the game that we're using is Frozen Lake, and it knows, you know, did you fall in a hole? Did you actually make it into a piece of ice that's going to take you to the cheese? Did you win the cheese? You know, obviously that would get you the maximum reward. Do you guys understand? All right, so this is very similar to the Bellman equation idea. And so, but you're going to minimize the difference between those two things, right? So it's essentially, I'll repeat here, this is the current state and the current action, and you just pick the reward associated with that. And that's going to be your QPred over here. And then you're going to compare this with target Q, which is kind of like where you are and where you want to be, right? So that's kind of what you're trying to optimize. So that's this target Q here, which is the future state, right? Plug it into the model, it gives you the vector. You take the maximum value there, which is the reward, and that's your reward here. So you add the reward that you got for this S1 plus this reward, and that gives you target Q. This is now, let's go to the Bellman equation, right? And think about this one a little bit. What was the Bellman equation? That was something that we covered last week, right? So in the Bellman equation, I mean, how did Bellman come up with this? I don't know. Genius. All right, but let's take a look. The Bellman equation should be in a simplistic form. See, this was the tabular data, right? If you look, it's kind of like this one, right? If you look, it's the update. So you had a reward, right? Oh, actually, where was it? Not that one. Here, this one's a little bit better, I think. If you look, remember that these LRs and Y, they're just parameters that you pick, right, on how you're going to update the thing. But really, the key thing to keep in mind is you have this reward plus this reward, which is associated with the future state Do you guys see that? So in the Bellman equation for the Q table, we would take the values of the original S and A, right? That reward, and we would update it by adding to it this whole term here. And you can ignore this part because it's just a normalization parameter. And this whole blue highlighted area is just made up of two things. The reward R that you got from the game, this one over here, and from the table, getting the reward associated with S1, the state in the future. So you take an action, you get a reward, plus the reward for that future state that you have in the Q table or from the neural network, right? You add those two together, and then we would use that to update the old state and action, right? That's how the Bellman equation works there. In this example, it's similar. So we take the reward here, and that's this reward, and we do add to the reward associated with the future state, S1. So that's this part here is essentially this exact same component. See that? But the difference is now we are like, instead of adding, right, we're taking the difference between these values. So you can see that here. So now S1, calculate QS1, take the max, which is the reward. This reward added to the reward that you got from the game, that gives you target Q, right? So this is your target Q over here. And now the other parameter is just the old state and action and that reward. And now you take the difference. Okay, and you're trying to optimize that in your loss function. Does this make sense, guys? Are there any questions? As far as this smooth L1 loss, as I said, we can look this one up on Google, but it's essentially like an MSC and an MBE, mean absolute. It should be maybe this. That. Yeah, so you can see the description here, but here is the whole thing. It's an if statement where it's either, you know, xn, xn, yn, yn. The difference between the two inputs squared or the difference of the two inputs in absolute terms, right? So this is like a smarter, you could just build an MSC and that may work also, or you can just do an absolute difference and that can work also, or something a little bit more sophisticated like this. The criteria for choosing this is going to be you set up some kind of a beta, and you know, so it's a might be a smarter way of doing it, but it's like an MSC. All right, so let's go ahead. That's the hardest part, I would argue, of this whole thing. So if you understand this, right, the loss function, and you understood the neural net, you can implement DQN, okay? So now, so that part is done. So now we take the difference, that's gonna be our loss, and then we can do something like zero grad, loss backward, and up step. These are the three heavy lifting statements that you see in Python for training, right? So this is from 520 or 365, pretty much the same thing. All right, so once this is done, the model is going to update the weights, obviously, try to minimize the loss function. And then here now we're just like collecting data, bless you. We're just collecting data, so we're collecting the rewards, right? We're keeping track of the reward count, the number of steps. Remember that we have to do this part, right? Once we're done with all that training, we make the, you know, we had an old state and a current state. Let's call it old, you know, S1 is the new state. So now the current state becomes S1, and we're going to repeat in the loop, essentially. Yeah. All right. And then we check also if D equal true, which means we either died or won, we break, right? So we break out of the for loop and so on. Here we have this epsilon plus delta, which should be related to, see, epsilon is being updated here, you can see. And that, where's this epsilon delta happening? We have, see, everything depends on this epsilon, right? So it needs to switch from choosing actions randomly to choosing actions from the neural net. But epsilon needs to be updated. Where's epsilon delta? It's in the top. Oh, that's right. That's right. That one. So that's just okay. So oh, it's negative. See that it's negative. So we're just decreasing over time. That's the idea. I get it. So that epsilon is going to decrease over time, right? And that makes sense. So it's like if the random number is 0 to 1, right? Sometimes it's 0.20, sometimes it's 0.80. So that epsilon is really high and it has a higher probability of matching it. But as we keep decreasing it, right? Epsilon might be 0.05 and my random integer is predicting 0.40. 0.40 is not less than 0.05. So over time, it's a clever way of choosing randomness. And instead you're switching to the model. Make sense? All right. So yeah, so that's essentially it. These two things are just collecting the data. So for instance, if D equal true, which means the game is over, and R is greater than 0, it means you have rewards, right? Then you collect in a list the number of successes. You also collect the number of steps taken to succeed per game. Else, use that you have a success list. The success list here, just keep in mind you're adding a 1, which means you won, or you add a 0 and it means you didn't, because the game ended, but your rewards were not positive. They were possibly 0 or negative. Got it, guys? Does that make sense also? All right, great. And then finally, we add for each game the reward total. So that would be the reward total per game. Okay. So that's it. That's DQN. So as you can see, very similar to Q-learning. We just changed two things. Instead of a table, we use a neural net and the loss function. Instead of the Bellman equation and updating the table, now we minimize the rewards essentially, right? With a loss function. Got it? Does that make sense? Any questions? All right, I'm gonna run this because we still want to view some of the results. So let me run it, hopefully. All right, it's training. So it has to do 4,000 games. While that's happening, we can copy some of the code. So for instance, here, I'm gonna copy this one. It's gonna take a while. So this will keep, we'll take a look at the number of, so the successes list is going to have about 4,000 entries in there. So there's going to be a lot of entries, right? And initially the successes are pretty bad, right? Initially. So all that we care about is like the last 100, in the list, because that's when the model should be better. So you should be able to recognize that this is just slicing, right? We're going to slice from just the last 100 essentially. And so for the last 100, you can see that there, last 100 epochs of success. We just want to see what was the percentage rate. So for instance, if we grab from 0 to 100, the first 100, you would expect that to be maybe 5%. I don't know, but you can play with it and investigate. But in this example, we just want to visualize the last. So since this is taking a while to train, we can actually look at the results here. We can see that when I ran this the last time, the last 100 epochs of successes were 70%. So it succeeded about 75% of the time. Okay. Maybe if you did a deep neural network, it would be 85%. I don't know, but you can play with that. All right. Then I'm going to plot these rewards. Okay. So I'm going to show you guys how I do this, it doesn't if you try to plot all the rewards go up and down, and it's sometimes not clear, especially if you have a lot of iterations. So what I usually do is I just take it in chunks of like 100, and then I just average it. And that should allow you to see things more clearly. So let's grab that code, and I can start describing it, and then hopefully the model will finish training, and we should be able to visualize it. So it's about 25% done at this point. All right, so let's take a look at this one. So you can see I'm just going to use a step size of 100. So every 100 entries, I will average essentially. You can see I'm using a list comprehension here. So for loop, so for I in range from 0 to the length of the list, but my step size is 100. So I'm going to grab 100, then the next 100, then the next 100, and so on. And then all I do is, so what do I grab? So I is the one that's changing. So then I'm going to grab from rewards list from I to I step size. So let's say I'm at position 200, then I would grab from 200 to 300 and slice that out. Okay. I'm going to notice that the parentheses is here. So I just add those and then average them or divide them by step size, which essentially is me averaging them, taking them. And then that's a list comprehension. So then I end up with R underscore RC, which is the average rewards over time. Okay. Then we can print all these values, rewards, what the values look like. But essentially what I wanted to do is I wanted to plot them. So, so that you can see that here. So, okay, I see that. So I was looking for RRC and I missed that. I did this. So I just assign R underscore RC to rewards list. So now what I do is here because I'm going to print a plot, I need values on the X and the Y axis. So I need this. I need in this one. So I just iterated through the reward list, grabbed every index and created a list of indices. So if I have, let's say, 3,000 values in rewards list, now in rewind or in REW also has from 1 to 3,000, the indices. And that way I can plot it. Does that make sense? So if I have 1 reward, 2 reward, 3 reward, all the way to 3,000 reward. All right, so I have these two lists, and I can essentially just plot my rewards. And again, the reason to do this is you want to make sure, let's say you were publishing a paper, right? What are the metrics that you show on your paper to show that your model worked? Well, this plot is very useful. So in reinforcement learning papers, this is something that is expected, right? That you are going to see this chart that the rewards are going up. They're a little bit different how it works. Got it, guys? Understand? All right. So let's see where it's at. So it's still training. It's halfway there. So we'll have to wait. But that's the idea. Okay, so, hopefully it'll give us this graph, which as you can see, there's about 40 entries. And the rewards, notice that they're negative initially. So actually it's pretty bad, right? The rewards that we've accumulated in the beginning, but over time, they started to go positive. And actually you can see there's an obvious trend here that the rewards are going up. Any questions about that? So over training, this is the lifespan of the training, and this is just the value, the average value, and we can see that it's going. These are just other charts like number of steps, etc. And then we did this last week. We can run this one also This is just no longer training, but instead just using the model, running it through the game, maybe 100 test games, and just seeing the results. Got it? So I want to run this part, but I'm still waiting for it to train. Yeah, so it's at 2400. Any questions so far? Yeah, please, sir. You want to see the game played out. So when I do, this is one of the reasons why I do taxi cab. So in taxi cab, I do have a way of showing you that things are moving. Um, the way that you can do this is as follows. You have to record every iteration, the grid. So it's almost like you have to record a movie. You see what I'm saying? And so this is what I will show. And I don't have it in this code, but in the taxi cab, I do have it. So as it's doing things, so let's go here. So as it's doing this, you have a list, and in that list, you're saving essentially a snapshot of what the states look like. And so that way, once you have that, then you can run that as a movie and see kind of the simulation of how it moved around. I don't know that I can do it in real time, but I can you can record how it did it. Yeah. So we'll see that in the taxi, and it'll make more sense. Mhm. Yeah. All right. So it's a 2600, 2800. So I'll have the taxi cab next week. Yeah. So after that, well, I guess I can copy this. What else? Yeah. Printing the statistics. This is just plotting some words. So you can do a lot with this, actually. It's not just for board games. As I said, well, this was used for the Atari. So there's a paper, I think it's by Emney, Atari RL. So if you remember, Atari is before Nintendo. It was like a game, a console from the 80s. And they implemented something like this in around 2013. So this was a very, important paper then. But essentially, so you can see how their thinking goes here, right? So they started with board games, which are two-dimensional, and they're thinking, what else can we do that's two-dimensional but more complicated, more impressive? Well, Atari. If you remember, Atari games were still two-dimensional games. They don't, not like today where you have three dimensions and it's just a different experience. These were, I don't know the official terminology, but they are basically like 2D games. Like you had Space Invaders. I don't know if you guys ever played Space Invaders, but pretty cool. All right. Back in arcades and things like that. Anyway, so these are two-dimensional games, and so they taught DQN models, I think something called a DQN or a DDQN, to play the Atari games, and they became really good at it. They were able, I think this paper talks about like, I don't know if it's in the title, but because there's several Atari games, like about 40, let's say. It's from DeepMind. See, is Volodymyr Mny, David Silver, who's very famous in reinforcement learning. And well, you can see here, actually, we present the first deep learning model to successfully learn control policies directly from high-dimensional sensory input using reinforcement learning. The model is a convolutional neural network. You can see why convolutional? Because the input state for them could have state data, but also you can concatenate images. And so as the image goes into the neural network, you can apply a convolutional layer. Do you guys understand what I mean? So to tie it to what we were doing here, you can easily concatenate an image to this, right? Right. So you can easily concatenate an image, you just spaghettify it, and it becomes part of the input. And so then the layers in here can have convolutions so that they can process images successfully. So the model is a convolutional neural network trained with a variant of Q-learning, whose input is raw pixels and whose output is a value function estimating future rewards. You can see it's exactly what I discussed today, except that the network has convolutions and the input images and the state vector is images. We apply our method to 7 Atari 26,000 games from the arcade learning environment, so like a gym type of a thing, with no adjustment of the architecture or learning algorithm. We find that it outperforms all previous approaches on 6 of the games and surpasses a human expert on 3 of them. So, and this was 2013, almost, is it 12 years ago, right? So think about that. This has been surpassed for sure. All right. But anyway, this brought a lot of popularity. And it was this paper in 2013 and then AlphaGo in about 2015. So if you know anything about games, like I don't know how many of you play chess, but humans were defeated in chess in the 90s or something. IBM did it when they created an AI computer called Deep Blue, I think it was called back then, right? And they had a competition somewhere, I can't remember exactly, but it wasn't a neural network. It was just like heuristic-based rules, like the traditional artificial intelligence, like for those of you that took 265, those types of methods. And so chess was, humans were defeated in chess back, a long time ago. Go apparently is like chess, but a much more complex game. And so I believe this paper happened in 2013, and then AlphaGo, which is the alpha agent that was really good at playing the game of Go. So that event happened in around 2015, where that model played Go against the world champion Lee Sedol, I think, from Korea, and the agent defeated the human, essentially. So that paper is really important. It was published in Nature and everything. But anyway, so you guys can take a look at the paper if you're interested. Very nice paper. Has more of the ideas, but it's essentially what I'm explaining. You can see here the same thing I've been telling you. You show the rewards, right? So this is expected in reinforcement learning papers. You plot the rewards. You want them to go up, essentially. And yeah, that's the paper. Okay. So let's see. Here. All right. So I think it finished. Seems like. All right, great. So it finished training. So now let's go ahead and print the success rate. Oh, 68%. So this time around, not as good as what I had. I believe, 75, was it? Yeah, 75. See, it can vary. Hey, do a deep neural network and see if you can get higher, right? So That's the point. Okay, so let's just finish. So we'll finish in a few minutes, and then we'll take a 10-minute break, and then you guys can do your exam one. All right, so we want to plot the rewards, so let's do that. There they are. As you can see, this looks a little bit different, but consistent. So it had a big jump. Like it's interesting, right? Think about the agent, right? It's learning how to play the game somehow over here, and then there's a big jump. It learns something about the game. Like it got some insight about it, and it's like, huh, because you can see there's a shift here, and then it's kind of consistent going up. That's an interesting observation. And then this would be just running. So now, just like we did last week, we run 100 test games. We're not going to train anymore. We just play the game and see how it performs. Same idea. Notice that you don't have the random thing anymore. You just give it the state. The model predicts. Then you get the index, and that index becomes the action. That action is given to the environment, which provides the future state plus rewards and things like that. So you can keep track of things. You keep track of these, and essentially that's it. So you play the game and you're just keeping track of the information. If you wanted to view this, as I said, you'd have to record in a list the states and so on. And I'll try to have that by next week. So now let's print it, and it says it got a 70%. Percent of won games in the test set was about 70%. Not the greatest, but evidence that it's learning. Yeah. All right. Any questions, guys? That concludes. So as I said, we're doing our track on reinforcement learning leading up to RLHF, right? And the newest methods. This we've done Q learning with the tabular Q learning, and now we've done Q learning with a neural network, right? So neural networks. These are the value-based approaches. Next week, we will switch over to the policy-based approaches, which are the ones that are used in the context of large language models. Okay. Any questions? Make sense? All right. So I will stop this video. You have, of course, the code provided on the GitHub. Just do that.